Hi, this is Mr. Swanson, and we're going to continue learning about chemical reactions, and we're going to dive into one of the main types of chemical reactions called combustion reactions. And we chose this one to start because I think it's the most interesting in terms of relevance to your everyday life. So we will learn just a little bit about combustion reactions. So during this unit, we're going to talk about 5 of the 6 main types of reactions: synthesis, combustion, decomposition, double, and single replacement. And if it's not one of those, we classify it as a redox reaction. So we're going to focus on those 5, and you would have learned a little bit about them in physical science last year. Now, right off the bat, we are going to give you a lot of information on the test. So this is the reference sheet that you will see on the test. And there you see that there's the 5 main types of reactions kind of listed: synthesis, decomposition, single replacement, double replacement, and combustion. And underneath them, there's subtypes. So, for instance, you could have a synthesis reaction with a metal halide, and we'll talk about what that means, how to recognize it. We'll talk about, the types of double replacement reactions, or that there's 2 types of combustion reactions. So you're going to use this reference sheet, and you should download it from Schoology so you have this kind of with you during the whole unit. Now, in general, a combustion reaction is a reaction with a hydrocarbon plus oxygen, and in the process, it produces CO2 and water. And so a lot of times you're going to see it written as CXHY. So that means, you can have any number of carbon and any of number of hydrogen. But you're also going to see, for instance, with the examples above, sugar. So it might be CH, and it might have an O in it, or it might have another O and an H, showing that it has an alcohol, or kind of a group that you find in sugars and stuff like that. And so you're going to want to recognize hydrocarbons right away as something that primarily has some number of carbons and some number of hydrogens, and all of these examples kind of have that. You're also going to see it reacting with O2 and produce CO2 and water, and just a second we'll talk about the case when it doesn't produce CO2 but instead just CO. So that's kind of the general formula for a combustion reaction. So this is taken right from the reference sheet, and we're going to be looking at the 2 main types, which are incomplete combustion, when you have insufficient oxygen, or complete combustion, when you have an abundance of oxygen. So you have plenty of oxygen. And you can see that the difference is, in a complete combustion, the only 2 products are carbon dioxide and water. In insufficient, where there's not enough oxygen, you also produce carbon monoxide. And that's just, carbon dioxide isn't great, but it's not great for the environment. But humans, we tolerate normal levels of carbon dioxide. We exhale carbon dioxide. But this CO, carbon monoxide, is it's very deadly and dangerous, especially in an enclosed building like a house or garage or ice house or something like that. So we're going to talk about these 2 main cases, where you don't have enough oxygen, where it's incomplete, and when you do, and it's complete combustion. So before we get into that, why don't you pause this and figure out which ones are combustion reactions. So you don't have to say if it's complete or incomplete, but find which ones in this list are combustion reactions, because just identifying the reaction type is important. So pause it, see if you can figure it out, and then I'll give you the answers. So here are the 4 combustion reactions in this list, and hopefully you didn't get tripped up on C10H16, because that looks like it is a hydrocarbon, but it's not a reaction with oxygen. So that is not a combustion reaction. And in all these examples, they were complete combustion. So when we say incomplete combustion, what are we really talking about? Well, I think it's easiest to take a look at a campfire example. So in a campfire, you're burning wood, and wood is essentially a hydrocarbon. So wood is some version of carbon and hydrogen, and there's of course other stuff besides just carbon and hydrogen, but that's mainly what it is. So you're lighting that on fire, and that wouldn't work at all, except for the fact that oxygen is in the atmosphere. And so, in the presence of oxygen, wood will burn, and in the process, it burns carbon dioxide. It produces carbon dioxide and water. And so, in a normal situation, there's an abundance of oxygen, and that makes this really kind of efficient fire. And those are the two products. But in reality, in a campfire, a lot of times you don't have enough oxygen. And one way you know that is because you have to constantly blow on the fire to kind of get it going. And when you blow on it, it burns kind of cleaner, it burns hotter. And so usually in a campfire outside, it's not complete combustion, because even though there's a lot of oxygen, it's not all getting into the fire because maybe of how you build it. So you're going to produce some carbon monoxide. And that's not the biggest problem because you're in the air and it disperses and it kind of spreads out. But if you're like in an ice shack or in your house and your furnace is, at best your furnace is like probably 91% efficiency. You might want to go home and look to see at your furnace or whatever. It should say somewhere on it. I think mine is about 85% efficient, which means it's producing some carbon monoxide. Now, the goal is we vent that carbon dioxide out of the house. But if the system is not set up right, or there's some other failure in the system, that incomplete combustion, that CO2 is going to build up in our house. And that's why we need CO2 detectors, because we don't want that buildup of carbon monoxide in the house. And so it's really hard to get a complete combustion. And so, like I said, even the best furnaces on the marketplace right now are 9-10% inefficient. So take a second right away and pause this and read this article, because this is an article from a hockey rink near the Wisconsin Dells where a lot of people are sick because of this incomplete combustion. So take a second, read, and come back. All right, so now that you read that, hopefully you can see that, this is a small enclosed, or an enclosed area, I guess not super small, but it's enclosed, well insulated. And so this propane generated, or this propane powered Zamboni was definitely not perfectly efficient. And so all the carbon monoxide is being trapped in this arena, and it poisoned a bunch of people. And you can't smell it. And so really you start feeling faint and dizzy and you can pass out. And so it's kind of the silent killer. So luckily there wasn't, huge problems, but we want to be mindful of carbon monoxide. Take a second to pause this article and read this, because this is another even closer to home article about somebody exploring a cave and having carbon monoxide poisoning. And a hyperbaric chamber is a chamber where they essentially try to regulate kind of the levels of oxygen in your blood after kind of having too much nitrogen or too much carbon monoxide in there. So take a second and read this, and hopefully you can understand why it's so important to have carbon monoxide detectors in every area of the house, in every room if possible. And that's now kind of building code that we need to have these detectors, especially in any area where people are living or staying regular. So why is carbon monoxide that deadly? And without getting into too much of the biology, is carbon monoxide kind of competes with oxygen in the blood. And so hemoglobin, which carries oxygen around your body, will end up binding to carbon monoxide instead of oxygen. So it's kind of poisonous because it stops oxygen then. It replaces, the spot where oxygen would be. And so now carbon monoxide is going through your blood instead of oxygen. So it's kind of a double whammy. Not only do you have something your body doesn't want, it's now lacking something that your body really needs. So it's this kind of balance or fight between the carbon monoxide and the oxygen. It might be good during the break to go around your house and take a look to make sure you have not just smoke detectors, but carbon monoxide detectors. And I would argue that carbon monoxide detectors are just as important, if not more important, than our smoke detectors. And because with a fire you can smell there's a problem, and usually there's a warning to get out. But with carbon monoxide, especially a lot of people are going to get it while sleeping, or kind of without knowing, and they're going to pass out. And so a lot of times there's not a warning, or there's not time to react when you finally feel sick. So we want to keep carbon monoxide detectors all throughout the house. And like if you go ice fishing, for instance, this winter, you want a carbon monoxide detector in there. And I brought one when I went ice fishing up in Mille Lacs last year. I brought my own carbon monoxide detector, and it definitely went out. And we had to call and get our furnace on the ice house fixed because it was just not working well. And so you want to, if you go somewhere to like a cabin, it's not even a terrible idea to bring that. So to kind of summarize everything, here's the two different reactions. And again, they're both hydrocarbons and they're both reacting with oxygen. It just depends on if there's enough oxygen or if there's not enough oxygen. And you can see when there's not enough oxygen, there's an extra product that's created. If there was super little oxygen, like if there was almost no oxygen as well, you would see carbon monoxide plus carbon dioxide plus just carbon plus water. And I can show you an example of when this happens. The next time you light a candle, and I guess do this very carefully, and as you are kind of like maybe putting a top on it, you're going to start smothering it. And what happens is as the flame is going out, there's not enough oxygen. And so carbon, that soot, that black stuff you see on a candle, that's carbon from this super incomplete combustion. So that's a time you might see that. So if you see soot on your fireplace or your candle, that's due to really incomplete combustion. So here you're being asked to predict the products. And so it says pay attention to the oxygen conditions. So here, propanol, C3H7OH, has abundant oxygen. So the reaction is going to be like this: C3H7OH plus O2 reacts to form, and then it's plenty of oxygen, so we know the products are CO2 plus water. Now, let's say you forgot. No big deal. We give you that equation sheet, and so you just want to reference that and use that, and there's a very little memorization you have to do in this unit. If we take butane, which you might recognize from like a lighter or something like that, without a lot of oxygen, you're going to have CO2 plus CO plus water. So you're going to have that third product. So you don't have to do these problems here. Instead, I just want to direct you to your packet, part 4. We're skipping around a little bit. And you want to try to do these problems. And we give the common name, like gasoline, and then the formula right there. And then we also tell you the oxygen conditions. So abundant, minimal, abundant, abundant. And so you want to take a look at that. And so this first reaction, for instance, is what's happening in your car. And so like when you are behind the car, you're going to see some gas coming out. Well, know that there's carbon dioxide. It's probably not perfect. So there's some carbon monoxide as well, which is why they say like don't start your car without your garage door open, because you're just pumping carbon monoxide into your garage, and you go out there and it replaces, like I said, the oxygen in your blood, and that's when you're going to get poisoned. So that's why, always open your garage door when you start your car. And so you also might see water drip out of the tailpipe. So you have some car, right? Here's a car, and then here's the tailpipe, and so you might see that water drip out of it in the winter, or in the summer when that water is condensing, and dripping down.